The West Sea in November does not concern itself with the ships that use it. The water runs between 3 and 8 degrees Celsius depending on depth. The weather systems that originate over the Manchurian interior produce a northwest wind that arrives at the Korean coast carrying the specific cold of continental winter, dry, sharp, without the mitigating humidity of oceanic origin. And the sky tends toward a shade of white that is not quite cloud and not quite clear. A flat luminosity that offers no shadows and no depth cues. Navigation in this environment is instrument dependent in a way that clear skies are not. The horizon is a suggestion. The distance to the North Korean coast at any given point in the West Sea is a number you know from the chart and cannot confirm from the bridge. USS Mahan makes 16 knots on a northerly heading, 38 nautical miles south of the northern limit line. She is part of the combined USROK response package that has been positioned in the West Sea following a North Korean ballistic missile test 46 hours ago. The diplomatic situation has been described by Washington as tense and evolving. The naval situation has been described by the commanding officer as "stay ready." The ship has been at elevated readiness for 36 hours. The crew is not fresh. They are professional, which is the thing that matters more than fresh when something happens at 2:53 a.m. The HY-2 Silkworm that the North Korean coastal battery fires has been in the inventory since the 1980s. It is large, slow by modern standards, and carries a 513-kilogram warhead that represents one of the heaviest conventional anti-ship warheads in the Korean People's Army Navy's operational arsenal. The Mahan's Aegis system detects the launch at 2:51:17 a.m. and assigns an SM-2 intercept immediately. The intercept geometry is clean. The Silkworm is subsonic, predictable, and the SM-2 has a high engagement probability against it. The SM-2 fires at 2:52 and 3 seconds a.m. It intercepts the Silkworm at 11 miles. The intercept is successful in the technical sense. The SM-2's proximity warhead detonates at 8 meters from the Silkworm's midship section and tears the missile's airframe into 3 major fragments and a debris field. One of those fragments, the forward airframe section, approximately 140 kilograms, including a substantial portion of the warhead casing and residual propellant, continues downrange on a flat trajectory at approximately Mach 0.7. The SM-2 intercept has not stopped the fragment. It has changed its target geometry. At Mach 0.7, the fragment crosses 11 miles in approximately 85 seconds. The Mahan's CIC tracks it as a residual debris contact. The fragment impacts the Mahan's port side hull at frame 54, approximately 1 meter below the waterline, at 2:53:28 a.m. The fragment is not a shaped charge. Its warhead did not detonate during the SM-2 intercept and does not detonate on the secondary hull impact. The fusing system's threshold was not met by the fragment's reduced velocity. What it is, at 140 kilograms, moving at Mach 0.7, is a battering ram. The hull plating at frame 54 is 19 millimeters HY-80 steel. The fragment punches through it cleanly, creates an irregular breach approximately 45 centimeters in diameter, and continues into the ship's interior before the structural frame at frame 56 stops it. The fragment comes to rest in the port main engine room. The flooding through the 45-centimeter breach at 1 meter below the waterline begins at 2:53:29 a.m. The rate of ingress at this breach geometry and depth is approximately 480 gallons per minute. The underwater pressure is sufficient to drive water through the breach faster in active sea conditions because the wave action periodically increases the effective submersion depth of the lower portion of the penetration. 480 gallons per minute in the port main engine room means the space reaches knee depth in approximately 4 minutes and waist depth in approximately 9 minutes. The port LM2500 gas turbine trips immediately on its water intrusion sensor at 2:53:31 a.m. One shaft offline, speed begins dropping. In those first 30 seconds, the ship begins to list. When a below waterline compartment on the port side begins flooding, water mass is added to the port side below the center of gravity. The effect is a rotational moment. The ship tilts toward the flooding side. The Mahan Stability Management System registers the developing port list at 2:53:44 a.m., 2 degrees. By 2:54 a.m., the list has reached 4 degrees. By 2:54:30 a.m., with the port engine room flooding at 480 gallons per minute, and the breach geometry expanding slightly as hull plating stress fractures propagate outward from the penetration point. The list has reached 7 degrees. 7 degrees is where deck-mounted equipment begins to slide. 7 degrees is where walking without a handhold becomes active effort. 7 degrees is where the OOD on the bridge notices that the horizon, already a suggestion in the West Sea's flat winter light, has acquired a tilt that is not atmospheric. 7 degrees is also 3 degrees from the point at which the Mahan's metacentric height calculation begins producing numbers that get worse rather than better. Because below a certain hull geometry, the restoring moment from buoyancy decreases faster than the healing moment from flooding increases. The dangerous number is 15 degrees. At 15 degrees, the Mahan Stability Book shows a crossover point. The ship's ability to right itself becomes dependent on active counter-flooding rather than inherent stability reserves. At 20 degrees, recovery is no longer certain without external assistance. At 28 degrees, the calculated capsize angle for this hull configuration, the ship does not recover. The list is 7 degrees at 2:54:30 a.m. The flooding rate is 480 gallons per minute. There is no effective patch solution for a 45-centimeter breach 1 meter below the waterline on a ship moving through sea swells in the West Sea at 2:54 in the morning. The breach geometry does not accept the standard wooden plug or speed patch approaches. A collision mat over an underwater breach requires diver operations or calm water that the West Sea is not providing. The P250 pumps in the damage control inventory can dewater at 250 gallons per minute each. 2 P250s running simultaneously produce 500 gallons per minute of dewatering capacity, which is theoretically sufficient to match the ingress rate. Theoretically, in an active flooding compartment with a running electric pump submerged in water, with debris from the fragment impact potentially blocking the suction lines, with the ship now listing 7 degrees and the suction geometry of the pumps affected by the tilt, theoretical capacity is not operational capacity. At 2:54:45 a.m., the chief engineer arrives in DC Central. The status board shows port engine room flooding, ingress estimated 480 gallons per minute, port LM2500 offline, port main switchboard at risk from water contact. List 7 degrees port and increasing. He reads it in 8 seconds. He does not begin with the flooding. He begins with the list calculation. The flooding cannot be stopped in the next 60 seconds with any available damage control resource. The list is being driven by the flooding and will continue until the flooding is stopped, which it cannot be in 60 seconds. If the list continues at its current rate of development, approximately 1 degree every 40 seconds, the ship will reach 15 degrees in approximately 7 minutes. 7 minutes is an engineering time frame, not an emergency rescue time frame. But the margin narrows with every degree, and the tools become less effective as the list increases, because the geometry of everything, pumps, valves, tools, footing, becomes harder to work with as the deck tilts further. The chief engineer's assessment completes in 14 seconds. He makes 2 calls simultaneously via sound-powered phone. The first call is to the flooding response team. Port engine room, breach at frame 54, 1 meter below waterline, 45 centimeter opening. Deploy both P250 pumps immediately. Do not attempt a breach patch. The sea state makes it non-viable. Your priority is maximum dewatering rate. Get both pumps in the water and running in 4 minutes. The second call is to the damage control assistant. I need the starboard ballast and compensation system status now. Specifically, JP5 Tank P6 transfer capability, current fuel state, and the time required to open the transfer valve from DC Central. This is the call that will define the event. The Mahan carries her JP5 aviation turbine fuel in 8 separate tanks distributed through the ship for stability management purposes. Tank P6 is the port side after fuel tank, currently holding approximately 38,000 gallons of JP5. Tank S6 is the corresponding starboard side tank, currently holding approximately 34,000 gallons. The difference in fill levels exists because the fuel management system has been running preferential port side consumption to maintain trim during the patrol. P6 is fuller than S6 by approximately 4,000 gallons. The chief engineer's plan, which exists in the damage control doctrine as a recognized but rarely executed procedure called counter-flooding for stability restoration, is to open the cross-connect valve between P6 and S6 and allow fuel to transfer from port to starboard under gravity, using the ship's own list to drive the transfer. The heavier the list, the faster the transfer. The more fuel that moves from port to starboard, the more the list is counteracted. At the current 7-degree list, gravity will drive JP5 from P6 to S6 at a rate of approximately 280 gallons per minute. 480 gallons per minute of water coming in on the port side. 280 gallons per minute of JP5 transferring from port to starboard under gravity. The net port side mass change per minute is 480 gallons of water added minus 280 gallons of JP5 removed. A net port side mass addition of 200 gallons per minute equivalent. Slower than the flooding alone, but still positive. The list will continue to increase, but at 1/3 the previous rate. This is not sufficient to stop the list. It is sufficient to buy time. The P250 pumps, if they achieve their operational capacity in the flooding compartment, will dewater at 250 gallons per minute each. 2 pumps, 500 gallons per minute. Against 480 gallons per minute ingress, the net becomes 480 in, 500 out, minus 280 JP5 to starboard. The port side mass is now decreasing rather than increasing. The list begins to arrest. This is the calculation the chief engineer has done in his head in 45 seconds. He did not draw it out. He did not run a spreadsheet. He did not consult the stability manual, which is in the bridge officer's locker 3 decks above him. He did it in his head in DC Central, with the ship listing 7 degrees and the status board showing red on 3 systems and the sound-powered phone in his hand. He gives the order. Open the P6 to S6 cross-connect transfer valve. I want gravity transfer running in 90 seconds. The damage control assistant is already at the transfer valve control panel in DC Central. The cross-connect transfer valve is remotely operable from DC Central. He opens it. The valve takes 22 seconds to reach full open. The transfer begins at 2:55:47 a.m. The list at that moment is 8.4 degrees. The flooding response team has been working the port engine room with the first P250 pump since 2:55:10 a.m. The suction line has been deployed. The pump is primed and running. The dewatering rate on the first pump is confirmed at 230 gallons per minute. Slightly below rated capacity because the suction line has encountered partial obstruction from debris in the flooding compartment, likely fragments of the hull plating driven inward by the impact. The damage controlman working the suction line adjustment cannot see what he is working with. The space is in emergency red. The water is now at mid-thigh, and the debris in the water is sharp-edged and invisible below the surface. He adjusts the suction line by feel. The rate improves to 245 gallons per minute. The second P250 is deployed at 2:55:51 a.m. The list continues to develop. 8.4 degrees at 2:55:47 a.m. 9.1 degrees at 2:56:15 a.m. The combined effect of the P250 dewatering and the JP5 gravity transfer has not yet overcome the net port side mass addition. The pumps and the transfer together are producing approximately 525 gallons per minute of port side mass reduction, against 480 gallons per minute of ingress. The net is now minus 45 gallons per minute on the port side. The flooding is being overmatched, but barely, and the mass already in the port engine room is still there, being dewatered at 45 gallons per minute net rate. The list will not immediately decrease. The mass is still aboard. It is just being removed slowly. The list rate of increase has stopped. The list is stabilizing. At 2:56:49 a.m., the list reads 9.3 degrees. At 2:57:15 a.m., it reads 9.4 degrees. At 2:57:52 a.m., it reads 9.4 degrees. The trend line is flat. The ship is not righting itself yet, but it has stopped listing further. The dangerous progression from 7 to 15 to 20 to capsize has been interrupted. The port engine room flooding team confirms both P250 pumps operating at 2:57:30 a.m. Combined dewatering rate: 248 gallons per minute first pump, 241 gallons per minute second pump. Total, 489 gallons per minute. Against 480 gallons per minute ingress, the net dewatering is now a positive 9 gallons per minute. The water level in the port engine room is dropping, an inch every 12 minutes at this net rate, but dropping. Plus, the JP5 transfer is still moving 280 gallons per minute of mass from port to starboard. The list begins to decrease at 2:58:20 a.m., 9.2 degrees, then 9.0, then 8.7 at 2:59 a.m. The ship is righting herself, slowly, using pumps to remove the flooding and a fuel cross-connect to redistribute mass. The commanding officer, receiving the DC Central status updates via 1MC, asks for a list trend report at 2:59:05 a.m. The chief engineer responds, list decreasing. Currently 8.7 degrees, trending towards 7. Both P250 pumps running, JP5 transfer active. Estimate list below 5 degrees in 14 minutes. Ship is stable. The commanding officer acknowledges. He does not say anything further. He watches the inclinometer on the bridge. The list decreases through the next 14 minutes as the chief engineer predicted. 8.7 at 2:59:00. 8.1 at 3:01:00. 7.4 at 3:03:00. 6.6 at 3:05:00. 5.8 at 3:07:30. 4.9 at 3:09:00. 4.1 at 3:11:00. At 3:13 a.m., the list reads 3.2 degrees, and the inclinometer trend line is still improving. The port engine room has dropped from waist-deep flooding to approximately shin depth. The P250 pumps are winning the battle against the breach. The JP5 transfer has moved approximately 4,200 gallons from P6 to S6. The transfer valve is closed by the chief engineer at 3:14:07 a.m. The stability restoration is sufficient, and the remaining P6 fuel must be preserved for propulsion. At 3:14:07 a.m., the moment the chief engineer closes the transfer valve, the Mahan's remaining fuel state is assessed. P6 now holds approximately 33,800 gallons, down from 38,000 at the start of the event. S6 holds approximately 38,200 gallons. Total fuel state, sufficient for approximately 19 hours of sustained operations at single shaft consumption rate. The port shaft has been offline since the port LM2500 tripped at 2:53:31 a.m. The starboard shaft has been carrying the ship at 11 knots. 19 hours of fuel at single shaft consumption rate is enough to reach Busan under the ship's own power. Marginally, adequately. The list at the close of the transfer valve is 2.9 degrees port. It will not return to zero with the breach still open. Some residual flooding continues through the LM250 dewatering cycle, and the mass asymmetry of a partially dewatered port engine room maintains a small persistent list until the breach is physically addressed. The breach will be addressed at Busan, not at sea. For transit purposes, 2.9 degrees is stable. The cost of the decision is calculated at 3:15 a.m. when the chief engineer reviews the updated fuel management display. The cross-connect transfer moved 4,200 gallons of JP5 from P6 to S6. Those 4,200 gallons are not lost. They are in S6, usable for propulsion. But the act of moving fuel for stability purposes has changed the ship's endurance calculation in a way that was deliberate and necessary. The 4,200 gallons were used as a stability tool rather than a propulsion resource. They did their job. The cost is that the fuel management situation is now more constrained, and any further stability event requiring additional counter-flooding will have less reserve to draw on. The chief engineer also evaluates what was not available as an alternative. The ship carries approximately 2,100 tons of potable water in a distributed tank system. Using potable water as a counter-flooding agent would require manual valve manipulations across 3 different piping systems and would take approximately 20 minutes to set up. The ship was listing at 7 degrees and accelerating when the chief engineer made his decision. 20 minutes was not available. 4,000 gallons of JP5 that could be moved by opening 1 remotely operated valve in 22 seconds was available. The choice was not close. By 4:30 a.m., the port engine room is dry enough for a damage assessment entry. The flooding response team, working in SCBA gear because the damaged JP5 fuel supply line to the tripped port LM2500 has been leaking residual fuel. A secondary problem the chief engineer addressed at 3:08 a.m. by isolating the port fuel supply. Enters the space and conducts the inspection. The breach at frame 54 is visible in the hull. A roughly circular penetration, the plating curled inward around the perimeter. The Silkworm fragment, 140 kilograms of steel and propellant residue, is wedged against the structural frame at frame 56. The fragment has not detonated, and the residual propellant is not presenting an ignition hazard. EOD assessment is requested for Busan. The port LM2500 has sustained water ingress to its lower turbine section and will require depot-level inspection before being returned to service. The port main switchboard, which the chief engineer had flagged as at risk, was protected by the aggressive early dewatering action. The water level never reached the switchboard's lower bus connections. The switchboard is inspected, found dry and operational. The Mahan transits to Busan at 11 knots on the starboard shaft, maintaining 3.1 degrees of port list throughout the transit as the steady state result of the partially flooded port engine room balanced against the redistributed JP5 in S6. The list is stable. It does not worsen. The fuel state holds. The ship arrives in Busan at 11:47 a.m. 1 HY 2 Silkworm airframe fragment, 140 kilograms, impacted the port hull at frame 54, 1 meter below the waterline. Hull breach, 45 centimeters diameter. Flooding ingress, 480 gallons per minute. Port LM2500 offline on water intrusion sensor trip. List progression, 0 to 9.4 degrees in 4 minutes and 22 seconds. 2 P250 dewatering pumps deployed. Combined rate 489 gallons per minute. JP5 gravity countertransfer. P6 to S6 via cross-connect. 4,200 gallons transferred in 18 minutes and 20 seconds. List arrested at 9.4 degrees. Restored to 2.9 degrees over 14 minutes. Port engine room dry enough for entry at 4:30 a.m. Starboard shaft only, 11 knots. Busan transit 19 hours. Fuel state, adequate. Ship status, operational. The post-event debrief at Busan identified the counter-flooding decision as the element that required the most explanation. because it is not a decision that appears often in damage control after action reports. The chief engineer was asked to walk through his reasoning. He said the breach could not be patched at sea in those conditions. The P250 pumps alone were not sufficient to arrest the list at the rate it was developing. And the cross-connect transfer was the only rapid mass redistribution tool available in the time window he had. He was asked if he had considered the fuel state implications before making the decision. He said he had. He was asked how long that consideration took. He said, less than the other parts of the calculation. He said it takes more time to second-guess a tool that works than to use it. He was asked if there was a risk that the transfer would overcorrect and produce a starboard list instead. He said yes, which was why he closed the valve at 3:14 a.m. rather than letting it run. He was asked how he knew when to close it. He said he watched the inclinometer. The inclinometer on USS Mahan, certified for service and never previously the primary instrument for a stability restoration decision under operational conditions, is still in place on the bridge. It reads 0 in port. It read 9.4 degrees at the worst moment. The difference between those two numbers is 4,200 gallons of JP5, 2 portable pumps, and a chief engineer who understood what a cross-connect valve was for before he needed it.